In this video, I'll be solving logarithmic equations. So here are some examples of log equations. Log equations are just equations that have logarithm expressions in them. So this first equation, there's our log expression. Here's the log expression, and then in this third equation, we have two log expressions. So the idea for solving a log expression is to convert, or first rewrite the log expressions as a single term. Okay, and then typically from there we will convert to an exponential equation to solve. This isn't always the procedure we need to take, and we'll see when we don't need to go through these steps. But for these first few examples, this is what we'll do. Okay, so first up we have 2 ln of x plus 3 is equal to 7. So what we want to do is isolate the log expression. So what I'm going to do is I'll subtract 3 from both sides, and then we'll divide both sides by 2. So we have ln of x is equal to 2. And then from there, so first off, we've isolated the logarithmic expression. So from here, we're going to convert this into an exponential equation. Ln of x means, remember, log base e of x. So the base is e, and the 2 is the exponent. So that's all we need to do for our answer. E is the constant 2.7181, etc., etc. So there is our exact value. So this is the exact solution. And if we had a calculator and we wanted an approximate solution, we'd get 7.3891, and that would be the approximate solution. All right, so let's look at a couple more examples here. Okay, so in this log equation, we have two terms that have log expressions in them. So what we want to do is we want to condense this into a single log expression. Because we're adding the two log expressions, we can use the product rule and combine the arguments by multiplying. Okay, and we've isolated, we have moved this down to a single log expression. So then we can just convert this into an exponential equation. The base is 2, 3 is the exponent. Okay, so from here this is a pretty straightforward equation. 8 is equal to 6x minus 10. 18 is equal to 6x. X is equal to 3. One thing we need to do when we're solving these types of equations is we have to check the solution. And what we're doing is we're checking that the solution doesn't give anything that would be outside of the domain for a log function. So log functions, the domain is always any positive number. So we can put in any positive number into a log expression or a log function, and it will be defined. So what we need to do is we need to check that our solution, in this case 3, we need to check that the solution, how would I say this, gives a value in the domain for a log function. Okay, so what we're going to do is we'll plug in 3 right here. So 3 times 3 is 9, 9 minus 5 is 4. We can take a log of 4. And then in the first log function, we have log of 2. There's no input for x that we need there. So that tells us that 3 as our solution does satisfy this domain check. Okay, and then there's another type of log equation that we could have, and this we can solve these types of equations with something called the one-to-one property. What the one-to-one property says is if we have a log base b of, let's say, s, that is equal to log base b of t, that means that s is equal to t. Okay, so if we have log functions with the same base on both sides of the equation, that means that the arguments must be equal to each other. So, for example, if we have ln of x squared equal to ln of 2x plus 3, we have two logarithms, each with a base of e, so that means that our arguments must be equal to each other. Okay, so we solve this equation, x squared is equal to 2x plus 3. And this is just a pretty simple quadratic equation. X minus 3, x plus 1, so x is equal to 3, x is equal to negative 1. Okay, and then we need to check those. So when I plug in 3 here, I get 9, ln of 9, so that's good. When I plug it in on the right side, I get 2 times 3 is 6. 6 plus 3 is 9, that's positive. So I get ln of 9 is equal to ln of 9, and that's good. And then let's plug in negative 1. I plug in negative 1 in for x and square it. I get positive 1, so I get ln of 1. And then on the right-hand side, when I plug in negative 1, 2 times negative 1 is negative 2, plus 3 is positive 1. So that is also good to go. Okay, and then this one here, we have 3 log expressions. If possible, we want to condense the 2 log expressions on the left, the 2 log functions, into a single log function. So we're going to use the quotient rule. We'll say log of 3x minus 2 divided by 2 here, and that's equal to log of x plus 4. Okay, so these are both log 10. So because these both have the same base, that means we can set the arguments equal to each other. So 3x minus 2 over 2 is equal to x plus 4. I'll multiply both sides by 2. I get 2 x plus 4 over here. Alright, so if I subtract 2x from both sides, I'm left with x. Then add this 2 over here. I get x is equal to 10. Okay, and then let's just check that. When I plug in 10 here, I get 28. There's nothing to plug in there. And then on the right side, I get log of 14. So I'm just looking to make sure that the arguments are positive, and that is satisfied. So looks like x is equal to 10 is our solution. And we'll finish up this video with 2 longer examples. The first says, the city of Morskietown, it's my favorite place in the world, had a population of 35 people in 1938 and has been growing exponentially at a rate of 2.5% annually. So we want to find a few different things. Write an exponential function that models this situation. How many people lived in Morskietown in 1990? How long would it take for the population of Morskietown to reach 300 people? And in what year would the population of Morskietown double? Okay, so for part A, we want to write an exponential function that models this situation. Because we're talking about population growth, we're going to say that this growth is continuous. And all that means is we can use this general form AE to the KT. So the key point here is that the base is the exponential constant E. Instead of f of x, I'm going to use m of t, m for Morsky, and then the input is going to be t for time. So m of t is equal to a. The a value is the initial value, so we initially had 35 people in my favorite town, and then exponential constant e, and then the growth rate is 2.5%, so it's 0.025t. So that's going to be our function. And t is the number of years after 1983. Okay, and 1983 is significant because that's when I was born. So for part B, how many people lived in Morski Town in 1990? So in 1990, that's 7 years after 1983. So we're going to solve for m of 7. So that's what we do. We just plug in 7 in for t, and we end up with about 41.7 people, 41.69 people. So we can just round that to 42 people. Okay. Part C says, how long would it take to reach 300 people? So this is a little bit more complicated. What we want to know is, when is the value of the function m of t going to be 300? So we want to solve this equation. 300 is equal to 35 e to the 0.025 t. And this is going to take a little bit more work. So this is an exponential equation. I want to isolate the exponential portion here. So I'm going to divide both sides by 35. We get 300 divided by 35 is equal to e 0.025t. Okay, so this is an exponential equation. And what we can do is we can rewrite this as a log equation. The base is e here. So if we rewrite this as an exponential equation, remember logs equal exponents, and the base here is e. So I'm going to use the exponential constant, ln, the natural logarithm, because there's an exponential constant. So ln of 300 over 35, logs are equal to exponents. So we're going to get this. And then lastly, we'll divide by 0.025. So ln of 300 divided by 35 divided by 0.025 is going to give us our amount of time in years. So let's plug this into the calculator. And doing so, we get 85.9374, let's call it. So this is asking for how long would it take. So t is about 86 years. So if I wanted to find out in what year that was, I'd say 1983 plus 86. And we get the year 2068. Okay, but it's asking how many years will it take. So 86 years is what we would get as that answer. And then the last one is asking, how long is this going to take to double? So let's think of our original function. And this 35 is the initial value. So in 1983, there were 35 people. So we want to know, when will this double? Well, it's going to double when there's 70 people in Morski Town. Okay, if we divide both sides by 35, we get 2 is equal to e 0.025t. Anytime we want to double an exponential function, this is the format we're going to end up with. We always get 2 is equal to the exponential constant raised to whatever the growth rate is. And then to convert this to a log equation, we're going to say ln of 2 is equal to 0.025t. So then divide by 0.05t. So ln of 2 divided by 0.025t, or 0.025 is equal to t. And more simply, anytime we want to know how long it takes a function or an exponential situation like this for the value to double, we always end up with ln of t divided by whatever the growth rate is here. And that'll give us the doubling time. So that's kind of a shortcut for us. So ln of 2 divided by 0.025, and I get t is equal to 27.7259 years. to double. All right, and then we're going to look at one more question. This says you currently have a credit card balance of $500, compounds monthly at a rate of 14.9%, which is actually pretty good if you can get a credit card that has that rate. Suppose you decide to not make any payments to the credit card for the next 5 years. Not smart. You want to be making your credit card payment. All right. Part A says, what would be the balance for the credit card after 30 months? Part B says, what would be the balance of the credit card? Or when would the balance of the credit card be $2,000? And then how long would it take the credit card balance to double? So this question doesn't ask us to find the function, but we should find the function that'll help us answer these three parts. So when we're talking about compounding interest like this, that is not continuous, we're going to use this function. So P is the principal, so we're going to have $500 initially, 1 plus the interest rate, 14.9%, so 0.149 divided by n is the number of times we're compounding per year, which is 12, raised to the 12t. So t is at the input of this function. All right, so first says, what would be the balance of the credit card after 30 months? Now we need to be careful here because this function that we wrote has t in years, so we need to convert 30 months into years. Well, each year has 12 months, so this comes out to 2.5 years. So how much, what's the balance of the account after 2.5 years? So we're just going to plug 2.5 in up here. Okay, and then we just type this into the calculator and see what we end up with. And what we get is about $724.02. Now, this isn't totally realistic because if you do not make payments on your credit card, you often get a fee. So while the balance might only be at $724.02, I don't know, my credit card, I think there's a $35 fee or something if I don't make a payment. So that would also be taken into account. And that would be bad because if you had a $30 fee times 30 months, that's almost that's $900 extra. So that really would hurt you. For part B here, it says, when would the balance of the credit card be $2,000? So we set the function equal to 2,000. What we need to do here is solve for t. So we're going to isolate the exponential portion here. So we're going to divide both sides by 500. 2,000 divided by 500 comes out to 4. And I'm going to simplify what's inside the parentheses there. Do I want to do that? Actually, we won't do that because we'll lose some information due to rounding. Okay, so we want to rewrite this as a log equation, and actually I will rewrite this part. That comes out to 1.0124, let's call it. So we're going to have log base 1.0124 of 4 is equal to 12t. So then divide both sides by 12. And so we're going to write all of this divided by 12. So how can we come up with an answer from the calculator for this? Let's see. Okay, well, let's see. Your calculator may allow you to enter any base value here to a logarithm, and if it does, then this is not difficult to do. If your calculator doesn't allow you to do that, well, you should use the change of base formula, and I'm just going to factor out the 1/12 here. So the change of base formula says, well, I can rewrite a log expression like this, as long as I have the same base here and here. Now 10 is usually what we do because log base 10 is what our calculator gives us. So take a moment, see if you can punch that in, and let's see what you get. Doing so, I get a t-value of 9.3741, so about 9.4 years would take for the balance of the credit card to be about $2,000. That's kind of in line with what we saw previously. After 2.5 years, the balance was $724. So if we keep growing, after about 9 years, we're going to end up at $2,000. Okay, and then how long would it take for the credit card balance to double? Okay, so for doubling time, if we're starting with $500, the doubling is going to be 1,000 here. So I'm going to divide both sides by 500. We get 2 is equal to 1 plus 0.149 over 12 raised to the 12t. Okay, so we want to rewrite this as a log equation. The exponent is 12t, so the log expression is going to be equal to 12t. The base here is this value, which we saw was 1.0124, and then the argument is 2. So we're going to divide this by 12. So I get log base 1.0124 of 2 divided by 12 is equal to t. So this actually looks very similar to what we had here. Okay, so we're going to go about this in the same way, 1/12, and then I'm going to use the change of base formula. So log of 2 divided by log of 1.0124. And let's see what that gives us. And I end up with 4.6871 years. So the balance of this credit card would be $1,000 after about 4.5 years, and that's in line with the rest of the values that we came up with. So we saw that after 2.5 years, the balance would be about $724. After 4.5 years, the balance is up to $1,000, and then after 9 years, the balance is up to $2,000.